Well, hello everyone. This is our March AI4C, Artificial Intelligence for Clinicians lecture series. And we are delighted to have Dr. Ian Pan with us today, who's going to talk about AI in radiology challenge accepted. And I think people will still continue logging in, but let's go on with the introduction. And as you know, this is a series that happens every second Thursday of the month from September to May. We take the summer months off. And you can see some of our past speakers there. Last month we had Pranav Rajpakar, and today we have Dr. Pan. In April, we have Dr. Trivedi from Emory. And note the May date is off cycle there. It's actually that first Thursday of the month for Dr. Tessa Cook from the University of Pennsylvania. Um, Remember that you can review all of our past recordings at the link there, and Carrie Ann has put the links for past recordings into the chat if you're interested, and also a survey there to please fill out. That will give us feedback as to what types of things you'd like to hear about in this seminar series, in this lecture series. And again, here are some of the links where you can find MGBAI, our website, and other educational activities there as well. So I am delighted to introduce Dr. Ian Pan. He received his Bachelor of Science in Applied Mathematics, Biology, and a Master of Arts from Brown University. And then he got his MD from the Warren Alpert Medical School, also of Brown University. He did an internal medicine internship at the University Hospitals Cleveland Medical Center and the Lewis Stokes Veterans Affairs Medical Center. He's currently a fourth year diagnostic radiology resident at Brigham and Women's Hospital. He's a former chief resident for us, and he's a future neuroradiology fellow. He's also going to be staying for that at Brigham and Women's Hospital. Dr. Pan's expertise lies really at the intersection of artificial intelligence and radiology. With a nearly decade, starting as an undergraduate, I believe, experience building AI applications for medical imaging. He's best known for his recurring top performances in AI competitions, most notably those sponsored by radiology organizations such as the Radiological Society in North America, including a top performance while he was a medical intern. So imagine that. He's a medical intern and he's competing in this challenge and was a top performer. And he also won at that time and the inaugural Educational Merit Award for the RSNA AI challenges, during which he wrote code for his competitors, his other participants, to use, explaining to them some of the nuances of medical images and wrote code for them to use in their solutions. He is a Kaggle Grandmaster for his consistent top performances in data science challenges, and that's a very big accomplishment. His current interests lie in model development, in implementation and validation, post-production monitoring, AI education for radiologists, and open science in radiology AI. And he's a sought-after expert, really, in radiology. So he does some consulting for Centaur Labs, MDAI, and DASA, which is in Brazil. And he's always happy to help his colleagues. And I can say personally that collaboration with Dr. Pan is an absolute pleasure. So today he's going to talk about AI in radiology, challenge accepted. So let me stop sharing, Ian, and away you go.
Sounds good. Thank you so much for that introduction, Kathy. I'm just gonna go ahead and share my screen. Okay, so we will just get started. I forgot to include my disclosure slide. I do some consulting work for some companies, but nothing is relevant to what I'm going to be talking about today. So as mentioned, I'm currently a fourth year radiology resident at Brigham. This is my last year, but I'll be staying on for another year of neuroradiology fellowship. And I've been building AI models for medical imaging specifically for about 10 years now, coming up on 10 years, which seems crazy. And then I like to participate in these radiology AI challenges, and that's really the focus of my talk today. I'm going to be walking through some of these challenges, highlighting why they're important, and also talking about sort of what to expect in the future, given the rise of generative AI, these large foundation and frontier models like ChatGPT, since I bet that's what everyone's thinking about these days. So, what is an AI challenge? It's basically a competition to determine who can build the best model for a given task. So the key components are first, you have to have a task that you want people to solve. And I'm going to talk about several of these. You need to have a data set that people can use to train the model for that task. You need to have some way to rank models, so some kind of quantitative metric. And sometimes this metric is not very intuitive or interpretable, but it's basically used to rank participants. Since in the end, it is a competition, you have to figure out who wins, who's second place, etc. And then there are rules. You might want to limit the amount of external data that people can use. So that's data that's not provided by the host, but sort of just available. You might want to limit the types of models that people can use as well to make it a little bit more challenging. So then why create an AI challenge? So you can get a lot of people to work on one task by creating a challenge for it because it sort of attracts, people who are interested on working on medical imaging, people who just like to do AI and machine learning. And you can also use this as an opportunity to determine what is the best possible performance I can get given the task and the provided data. And in order to achieve this, you have to attract a lot of people. And for radiology specifically, not a lot of people in the tech space have the opportunity to work with medical imaging because it's typically siloed in hospitals. There's a lot of privacy protections around it because it is patient data, and rightly so. But that means that a lot of people are not really interacting with this type of data. And then also during the course of a challenge, there's a lot of knowledge sharing. Reproducibility is a big thing about challenges because a lot of them require you to open source your code and your models. So everyone can see exactly what you did to achieve the result. And then also opportunities for future research. So typically these data sets are still available for download. So anyone can download them, just have to cite the data set. You can work on your own problems, you can build your own models on them, and you can work on non-AI related stuff too, where this data might be relevant. So the RSNA AI challenges started in 2017, and they basically have had at least one every year since then, which is very impressive considering how much effort it takes to organize this. And you'll see a little bit of that as I talk about them. So there's an organizing committee. They decide what task that they want the challenge to be about. They design the metric. They determine how much data they need. They coordinate the data collection effort, often from multiple hospitals across multiple countries, determine the timeline for the competition. And then they need to annotate all of this data for the specific task. And this is like thousands or even tens of thousands of, x-rays or CTs. And it's basically volunteers who are annotating this data, which I think is very impressive. So this is a list of, I'm pretty sure I have all of the RSNA AI challenges that have happened and will happen later this year. So starting in 2017 with pediatric bone age assessment, then we started getting into cross-sectional imaging with CT, a little bit of MRI, screening mammography made an appearance as well about 2 years ago. Most recently, we had lumbar spine degenerative disease classification, and then this year, it seems like it's going to be brain aneurysm, which as future neuroradiologist is a particular interest to me. So hopefully I'll have a little bit of time to work on that as well. So these numbers here represent sort of my ranking or my team's ranking for each of these competitions, as well as the total number of participants. So I've been able to do quite well in several of these. And once you've done several of these, you kind of figure out like a workflow that works for you, and you kind of just recycle that over and over again. I've had the opportunity to team up with really bright individuals who I otherwise would never have the opportunity to work with. And so several of these high performing instances were with teammates. And we'll see what happens this year. You'll notice that there was a pretty huge jump from the first competition to all of the subsequent competitions. And the reason for that is RSNA decided to start hosting these competitions on a data science competition website called Kaggle. And I think this is owned by Google, I guess Alphabet, but it's a very large platform that hosts these competitions. And so it attracts a lot of people, and it's probably the most well-known platform out there for these kinds of challenges. So we will just dive right into the first challenge, which is pediatric bone age. And so the task is quite straightforward. You have a pediatric hand radiograph and you predict the bone age. And so right now, the way that works is we have an atlas that's 50, 60 years old, written by Gulick and Pyle. It has radiographs, sort of example radiographs for what the bone age or what the hand radiograph should look like for bone ages, and that typically spans like every 6 months or so. Um, and then the radiologist basically looks through these images, compares it to the one that they're looking at, and then determines which one is most similar, and then uses that to determine the bone age. So it's pretty much as close to like a strict pattern matching task in radiology as you can get, because you're just trying to figure out which image the one in front of you looks like out of a sample of images in a very old book. And so this data set had over 14,000 radiographs where they were able to get labels from the radiology report, um, and then provide this to the participants to then train their models. And actually, the test set that they used to determine the final ranking was rated by 6 radiologists. So about 200 radiographs rated by 6 radiologists, so that they could really get, a good gold standard measurement, since there is variability in terms of what people will say for a given radiograph. And the top solutions here achieved a mean absolute error of about 4 months, which is pretty good. So that's, less than like zero point 0.4 years. And so the cool thing about having these competitions is they release this data set and then you can build your own models and you can put these models up wherever you want. So I use this platform called Hugging Face. There's a lot of AI models on Hugging Face that you can use and interact with. Um, and most of them are not radiology related and pretty cool. So I recommend checking it out. But this is a bone age model that I trained on that data set. I uploaded. And so this is an example. So you can upload any bone age radiograph here by taking a screenshot or whatever. And then you choose the sex of the patient, determine if you want a heat map, which basically tries and shows you where the model is looking at when it makes its prediction. And then it tells you what the estimated bone age is from the prediction. And so, this is just for research purposes and not for clinical use. But I have heard people who have used this model and have found it to be quite good. So if you want to play around with it, feel free. So we'll move on to the next challenge, which was pneumonia detection. And so here the task was, you have frontal chest radiographs, predict the presence of pneumonia and draw a bounding box. So for the radiologists out there, can't really diagnose pneumonia strictly off of a chest radiograph. It just looks like an airspace opacity, which could be many things. And so essentially this was more of an opacity detection task than a pneumonia detection task, since we didn't have any clinical data. And this was the first competition hosted on Kaggle. So, over 1,400 participants or 1,400 teams and even more participants. And this also had the additional challenge of localization. So on the prior challenge, you just predicted a bone age. That's just a number. In this challenge, you had to say whether there was an opacity, and then you had to draw a box around it, and you would be evaluated on how good your box was in capturing that opacity. So a little bit more complicated there, but also more interpretable for anyone using the model, because now you have a box drawn around the finding of interest. And here we had over 20,000 labeled radiographs. And I just wanted to note that this competition had a strong radiology presence among the top 10 here. So I was a medical student at the time, but I was working in a radiology lab and I was planning on doing radiology. My teammate was a radiologist in Canada. Phil Chang is a radiologist. I believe he's still at USC. He competed on his own, did quite well. 16-bit was founded by 2 radiologists. They actually won the Bone Age Challenge. And then the 10th place team was a coalition from Brazil, also comprised many Brazilian radiologists, which was pretty cool. And so this is another example of a model that I trained on that data set, which I then uploaded on Hugging Face along with some other chest X-ray models. This X-ray on the left is actually my own chest X-ray when I had pneumonia a couple months ago, which was not fun. But you can see that the model I trained on that data set from the challenge does very well in localizing that airspace opacity. So at least for my case, it seemed to generalize pretty well. So moving on to the next challenge, which was intracranial hemorrhage detection. So given a head CT, predict the presence of any intracranial hemorrhage on each slice, as well as the five subtypes. Epidural, subdural, et cetera. You see them written out there. This was the first challenge with cross-sectional imaging. So the data set was much bigger, a couple hundred gigabytes. Here, over 25,000 labeled head CTs. So people actually went through all these head CTs. It was split up, of course, across many people, but they would go through each slice and then label the presence of hemorrhage and the subtypes that were present. So a pretty daunting annotation task. And this actually led to the development of some pretty novel architectures, I think, in terms of how to approach modeling with cross-sectional data, right? Because it is three-dimensional. But most of the top solutions, what they did is they treated it like a sequence of images. So you could treat it as like a 3D cube or a volume of images, or you can say each image is an element in a sequence, which is more similar to how we approach language modeling. And so you can use a convolutional neural network, which is very good with images. And then a lot of people use recurrent neural networks. You can also use a transformer, which is what most large language models use today to basically perform the sequence modeling because they do very well on sequences. And I actually use this architecture in pretty much all of my cross-sectional imaging projects these days. I'll usually experiment with a couple of variations, but it's a really powerful way to model these images. And, a lot of this came first from this challenge. And here, what I'm showing is a data set called MBH-SEG. And so the prior data set was not annotated with segmentation masks. I mean, imagine trying to segment out hemorrhage on 25,000 head CTs. Not all of them would have hemorrhage, but even trying to do it on 1,000 would be pretty significant amount of effort required by radiologists who are probably already very busy with their clinical work. And so this was not done on the whole data set. It was done on a couple hundred. But I show this because it's an example of how we can enhance existing, publicly available data for future tasks, right? And so something I'm working on now is using this data set to try and automatically segment all of the hemorrhage cases in that data set. And that way, instead of just having a model that says, here's hemorrhage in the CT, here's hemorrhage on this slice, it actually shows you where it is. And that can be more helpful in getting radiologists to use it, to trust it, and to buy in. So the next task was pulmonary embolism detection. And so it's similar to the intracranial hemorrhage one where we were trying to predict presence of pulmonary embolism on each slice in the study. But we're also predicting a lot of exam level labels, such as whether it had acute or chronic PE or both, whether there was right heart strain or evidence of right heart strain, whether it was a central or non-central PE, or maybe both were present. And so you'll see that a lot of the top solutions actually adopted a similar approach to the winners of the prior challenge, including my own. And this was actually the one I did when I was an intern. And so the only way I was able to do that was because I had a pipeline in place where it was pretty straightforward for me to run experiments. And so, I run an experiment and then wake up the next day, check on the results, run another experiment before I left for work, check up on it when I come back from work. And so it's not as impressive as it sounds. And then another thing that I'm highlighting here is just an article published in Radiology Artificial Intelligence, where similar to the segmentation data set I showed, they basically augmented this data set with bounding box annotations of the pulmonary emboli. So again, localizing the pulmonary emboli in the study so that we can have some way of being a little more interpretable in our model building by actually being able to show the user where we think the pulmonary embolism is. And it also gives you a stronger label to train your models with because now they're not just sort of guessing where on the slice it is, they're actually shown precisely where it is. So the next challenge was on brain tumors. So here, what we were trying to do was predict the MGMT promoter methylation status using MRIs of patients with glioblastoma. This is hard. If you ask a radiologist to look at a GBM and say, do you think the MGMT promoter is methylated in this tumor? They will have no idea, right? Or maybe there can be some signs that might point you into one direction or the other, but it's not an easy task. And that's why we require tissue to be sent to the pathologist and so that they can actually do the testing. And so this was the first challenge with MRI. It was done in conjunction by one of the recurring brain tumor segmentation challenges, which have been going on for a long time. And here we actually did not have that much data. So you'll notice that in for the intracranial hemorrhage competition, 25,000 head CTs, pulmonary embolism, 12,000 CTs. Here we had less than 600. And for a very hard task, this made it very challenging to build an effective model. And so the winning solution achieved an area under the curve of 0.62. This is a value that ranges from zero point 0.5 to 1, where zero point 0.5 is basically no better than flipping a coin. So here we're slightly better than flipping a coin. And I think this just kind of showed that this is a very hard task. The amount of data probably was not sufficient. And as someone who participated in this challenge, it was difficult to sort of get a sense of how my models were doing because basically I try and set up a validation scheme when I participate. And so, how do I know that one model is doing better than another, right? People might have heard of cross validation or things like that. And so, if you have an unstable cross validation scheme where your numbers are bouncing all over the place, then you really have no idea what's working and what's not. Models are very prone to overfitting. So it becomes quite a challenge to build a good model. And what you'll notice if you look up MGMT promoter methylation status, deep learning, MRI, glioblastoma, you'll find papers that report fairly high performance. And those were probably a little bit over optimistic because we had I think, over 1,500, close to 2,000 people participating in this challenge, and this is the best that we could get. And so, again, just highlighting what a difficult task this was. Subsequent challenges are pretty similar in terms of the nature compared to the prior, so I'll just highlight them briefly. So COVID-19 detection, that was in 2021, I believe. That was maybe like 4 years ago now, which pretty crazy to think about. And basically, we were tasked with predicting different patterns of pneumonia. So, COVID-19 pneumonia had a particular appearance on chest X-ray versus maybe like a lobar bacterial pneumonia, typically bilateral in the lung bases, and then also localizing a box or the opacity with a box in chest X-ray. So similar to that initial pneumonia detection challenge, cervical spine fracture. So we're trying to predict presence of fracture in the cervical spine on CT. Screening mammography. This was a little bit interesting, right? Because when we read screening mammography, we are just looking for suspicious findings that we might need to call back the patient for additional imaging. So we have something called a BI-RADS score. On a screening mammogram, we give BI-RADS score of 0, 1, or 2. 1 is negative, 2 is benign, 0 is call the patient back for additional imaging. So basically, we see something, we're not sure what it is. Maybe it could be cancer. Let's get some more imaging. The way they designed this challenge was they actually fast forwarded and went to see which patients had actual biopsy and what the result of that biopsy was. So, was it actually cancer? Then traced it back to the screening mammogram for that cancer. And the task was actually to predict whether there was cancer on the screening mammogram. So, we weren't predicting BI-RADS. And if you go to my Hugging Face profile, I actually uploaded a model that I trained for this competition as well that you can sort of play around with. And then later that year, we had abdominal trauma, predict presence of low, high grade liver, kidney, and spleen injuries, bowel injury, extravasation using CT, also a very interesting challenge. And then most recently, we had the lumbar spine degeneration challenge. So for those of you who read lumbar spine studies, sometimes it can be quite tedious. And you go in level by level, looking at the foramen, the subarticular recesses, and you know, the spinal canal, trying to grade mild, moderate, severe, mild to moderate to severe. And so this was just kind of trying to tackle that from an eye perspective. And so we have people who labeled each level, the foramen with mild, moderate, severe, trained a model to see which ones were most accurate in terms of predicting that. And what I really like about these challenges is it's not like you're just working in a vacuum. So there's a pretty active discussion forum. This is for the PE challenge. You know, people are posting their solutions when they win. People are posting their code when they win. People are posting, introductory things. I posted something here about pulmonary embolism because a lot of people participating don't have a radiology background and just kind of explaining what we're doing here. People are posting pipelines to experiment, uh, how to train a three-dimensional convolutional neural network, maybe where you want to start. And so there's a lot of knowledge sharing going on in these competitions. People are trying to win and do well, but that doesn't mean people aren't also trying to help everyone else out and trying to, make sure everyone is being able to take advantage of the competition to further their learning and do whatever they want to do with it. There's also something called notebooks. And so notebooks are essentially an interactive way of coding notebooks. So people will post these notebooks that basically show you in code how to do things. So one of the most popular notebooks for this competition was pulmonary DICOM preprocessing. So radiology images are stored as DICOM files, which if you're not used to working with can be a little bit unintuitive. And so just showing people how we extract the actual image data, what the metadata looks like, what things might be important to know when you're working with this data. People show you how to train models. People will do exploratory data analysis to give you an idea of, what's going on in the data. And so again, just highlighting that, there's a lot of knowledge sharing going on here and that it's actually a really great learning opportunity, even if you're just starting out and feel like, maybe this is too much. It's still a great place for you to play around and maybe if you're interested in gaining more hands-on experience and seeing how it's done. So I'm going to move on and talk a little bit about generative AI. So you'll notice that all of these challenges had quite specific task definitions, right? You know, uh, predict presence of hemorrhage and what subtype it is on each slice, right? Predict pulmonary embolism, lumbar spine degeneration. You train a model on a task, and that's basically all it can do. I'm sure most of you are familiar with chatbots and things like ChatGPT, DeepSeek, Grok, Gemini, Claude. There's deep research. There's a lot of things that are coming out these days that feel like they can do everything. You ask it a question, you ask it to write code, you ask it to solve, like International Math Olympiad math problems, and it's doing all of those close to, at, or even above a human level, which is pretty crazy. And so, the question here is, will we ever get that in radiology? All these big tech companies are working on artificial general intelligence. So AI that can basically do what a human does. And, Sam Altman at OpenAI is talking a lot about artificial superintelligence. So not just doing what a human can do, but doing things better than a human can do, which is kind of scary if any of you have watched Terminator. Um, and in radiology, this is basically an AI that can be a radiologist. They can look at an entire imaging study, doesn't matter what it is, right? Multi-sequence, like complicated MRIs, multi-phase, dynamic contrast enhancement MRIs, multiple planes. They can look at priors. They can look at, if you're looking at an MRI, they can compare it to a CT. They can integrate the clinical history. They can generate a full report, maybe even annotate the images with measurements and segmentations and potentially do this better than a radiologist, which sounds pretty crazy for people who have been doing this for a long time. Even myself, I've only been doing this as a resident, and it sounds pretty. Some of the things that these foundation and frontier models are able to do these days, it doesn't sound completely far-fetched. And so it kind of begs the question, why do we keep trying to build these task-specific narrow AI models when it seems like the future is much, much bigger? Like, is this kind of an outdated way of approaching things? And so there are a couple ways you can look at this. So training these large models requires enormous amount of compute and data. The average person cannot train a foundation model, right? You can't just train ChatGPT on your home computer. I participate in these challenges with a computer that's actually right next to me that I built myself. Um, it wasn't cheap, but it was still affordable enough on a resident salary. And so I could not train a foundation model on that computer. And when DeepSeek came out with their model, DeepSeek R1, which was quite competitive with OpenAI's model, part of their claim to fame was we trained this using much less money than a lot of these other models require. And when you look at just the cost of training it on a GPU, like not even all the additional overhead and R&D costs, it was still several $1 million. So that's what it means these days to cheaply train a foundation model. So narrow AI is easier and more accessible to train and deploy. So if you have something that's a pretty straightforward task and it's not too hard to collect the data, and you want to just integrate it as part of a larger pipeline, like for example, I just want to classify CT scans into what they are, like head CT, chest CT, abs and pelvis CT. That's pretty easy to do. You don't necessarily need a huge foundation model to do that for you, right? And you could probably train a model to do that pretty quickly, and it's not too hard to get that data labeled. And maybe you're doing this so that you can correct errors in the metadata or whatever like that. So it's part of a larger workflow. I will note that foundation models are capable of what's called zero-shot learning. And what zero-shot means is the model has never been trained to do this, but when you ask it to do something, it actually does quite well, right? So like I could show ChatGPT potentially an image of a head CT and ask, what is it? And it's never been trained specifically to classify what type of CT examination this is, but it will probably correctly tell me that this is a head CT or a brain CT, right? So if you don't have a lot of labeled data and you're just trying to figure out a way to automate a process, then a foundation model could be extremely helpful. And you don't have to run it on your own computer. You just have to pay for it, depending on, whether you have a subscription, whether you're doing it like per API call or things like that. Another thing I'll mention is when you read a lot of these papers, they will compare the more generalist models to task-specific models. So let's say I have a model that can, it's a foundation model for X-ray. So it can read any type of X-ray. And then I have a model that I trained specifically to look at pneumonia. Then, a lot of these papers will compare the performance of that more general foundation model for X-ray on pneumonia and compare it to the task-specific one and say they're actually very similar, right? So this model can read all X-rays and it can do it as well as a model that's trained only to look for pneumonia, at least for that specific task of pneumonia. And so it can serve as a benchmark for future models. And I think, these data sets are still useful for benchmarking performance of these models on these tasks, right? If you want to see how well your foundation model does on classifying lumbar spine degeneration, you can download that data set and you can try it out and see how well it does. And it can also be used for other areas of non-AI research, which I kind of alluded to earlier, right? Maybe you need a bunch of lumbar spine MRIs for your project. Well, this data set is available for you to download and to use. And so in the future, I would expect to see challenges which encourage users to take these existing foundation models and leverage them in unique ways to accomplish certain tasks. So there are open source foundation models out there that if you have a fairly powerful computer or not even a super powerful computer, you can download it onto your computer and you can run it locally. So you're not paying per use. You're not paying for a subscription. And generally, the companies aren't releasing their cutting edge models to the public, right? Because, they want to make money. But a lot of these models are still really good for a lot of tasks. And so if you're sort of more tech savvy, maybe that's one way you want to go. But all this to say, the future challenge may be, use like a foundation model to try and predict, certain pathologies in certain scans or something like that. Or maybe, it'll be sort of more open-ended and some people will be using foundation models and some people will not. And we'll still be doing things the conventional way. Because if you try and organize a challenge where your challenge is, okay, train a model to generate radiology reports on these scans, not many people have the ability to participate in that type of challenge, just because, as I mentioned earlier, the amount of compute and just the data storage requirements in order to do that. And so then you sort of already limit your potential audience. And a lot of the people who, or the companies that have the capacity to do this are probably working on things, related to their bottom end and aren't going to be participating in these. So that's also something to think about in terms of organizing challenges and such. So the main takeaways here, I think, are if you're stuck on an AI problem and you have the data and you're okay with, putting it out there for people to work on, you can consider hosting a challenge. On Kaggle, a lot of these challenges come with sort of ranking points and medals and prize money, but there are also a lot of community challenges. They don't gain as much traction, but you can still get, 100, 200 people working on them, where you don't have to give anything in terms of like prize money or anything like that. And then, you can just see what the larger community can do. And a lot of times they uncover things that you weren't thinking about or notice things in the data that you didn't notice. And if you're interested in gaining more hands-on experience, just consider joining a challenge. You might have no idea what you're doing and it doesn't really matter. I think a lot of people are kind of intimidated by the idea of doing this, but if you approach it in terms of this is just a way for me to further my own learning and my own knowledge, then just go for it. If you work on it for a couple of days, decide it's not worth your time, you don't have to keep doing it. You can just follow along peripherally and see what people are doing, and maybe apply some of that to your own work. And, I'm a big open source person. I like to train models on public data. I like to put those models out there for people to play around with. And so challenges obviously encourage that because you have to post your solutions, you post your models, and the data remains out there for people to use. And then also knowledge sharing, as I show with the discussion forum and the notebooks that people post, and also unlikely collaborations, right? So the most recent lumbar spine degeneration challenge, my team won second place. One person was a data scientist in Vancouver in Canada. Two of them were in Japan. One of them I had worked with previously. And so these types of collaborations wouldn't have happened outside of these challenges. And it's not about winning, it's just about having fun and learning. And this is something I have to remind myself about because there was a period of time where it started to feel like a burden where, I was participating because I wanted to win and I felt like I had to win. But now I'm sort of just approaching it in terms of, like it's just a way for me to exercise my brain and keep my skills up. And if I happen to do well, then that's great. So that concludes my talk. I wanted to leave some time at the end for potential questions or discussions. This is some of my contact information if you're interested in reaching out. I also link to my Hugging Face profile if you're interested in seeing what kind of models I'm putting out, and maybe some of those will be useful for your own work as well.
Well, thank you, Dr. Pan, for a wonderful talk and for all of your efforts. Fantastic. Thank you for outlining that. Full disclosure, I am on the RSNA Machine Learning Challenges Committee, so I have been involved in the committee that puts on those challenges from the beginning, the ones that you've participated in through the Radiological Society of North America. And I forgot to mention, and Khalid Yunus has reminded me, that you were one of the top 10 winning teams from the 2019 SIM ACR Pneumothorax Challenge. So I'm sorry I missed that. And thank you, Khalid, for reminding me. Folks who have questions, please put them in the chat or in the Q&A, and we'll have Dr. Pan address them. Um, One question that has come up that we'll address in a second, and people are saying thank you. I think it's wonderful that you outlined a number of things. The reasons for the challenges is how do you compare models? If people have trained them on different data sets and so on and so forth, and this is a way to get a performance metric in a sense And I love that you highlighted that it's really about team science and that in these challenges, we watch the chat as these challenges are going on while they're still open. And it's very interesting to see there are people from data science who maybe have very little understanding of the medical application, but they're very good data scientists and folks who are on the medical side who want to learn more about the data science, and it's been a wonderful activity. I love that you brought up what I kind of call the biologically inspired solutions, if you will. Recurrent neural networks, transformers, really those kinds of architectures originally have come out of text processing or natural language processing. And they were applied. It was very interesting that they were applied when we started using the cross-sectional imaging challenges that folks saw, well, it's a sequence of data. It's zeros and ones. It's a sequence. It's not text, but there is importance in one slice to the next from a medical standpoint that we can take advantage of these architectures that were used, and also that we were kind of the Bratz challenge, the brain tumor challenge where results were kind of equivocal, I have to say, and were it was somewhat, it was a very challenging activity, and it's an activity that a number of organizations have been trying to solve with small data sets. But that was kind of one of the challenges where we kind of scratched our head, and we tried to validate some of the models that had much higher performance. And that was part of the reason for doing this challenge. And we were unable to validate that some of the published results that showed much higher results. So I think that was very, very interesting. We have a question here. Has anyone tested the consistency of the winning approach, i.e., will it be the same winner if applied to a second unseen data set? And these are the challenge activities do have a holdout test set. But go ahead, Ian, Dr. Pan, if you wanted to address that question, checking the consistency of the winning approaches on unseen data.
Yeah, so I think the organizing committee has been starting to do this. I think a cervical spine fracture paper was recently published, which basically took all of the winning solutions from that challenge and then tested it on an external data set to see how it did. I believe it was published in Radiology AI. And that's the most recent one I can think of. I think they're also trying to do it for the abdominal trauma one. And typically in those studies, the winning solution is still doing the best. There's a little bit more variability though across sort of like if you look at the top 10, like maybe eighth place drops to ninth, or maybe like sixth place goes up to fourth. It also kind of depends on sort of what the initial difference of the winners were. So for some challenges, the difference between first and second
It's
is
minuscule.
bigger than in others. And in some, it's very tiny and it's just basically random chance, right? And so, um, a lot of times, if you run like a statistical significance test, for example, on these, like it would not be a statistically significant difference, like across like maybe the top, five solutions, for example. But typically, they all do quite well, but they tend not to do as well as on the original data just because that's kind of the nature of AI these days, a little bit of a generalization gap when applied to an external data set.
Yeah, yeah, absolutely. And as Dr. Pan mentioned, the committee has it for some of these challenges and is in progress for the abdominal one, taken some of the models and applied them to either their institution. And this committee is multi-institutional and it's international, actually, includes representation from international and they've taken some of these models and tried them on other data sets that may be a single institution or multi-institution that were not part of the challenge, and you should see some of those in publications. And as Dr. Pan outlined, putting these challenges on, the first year we did one challenge, and it was in preparation for months. And Dr. Pan rightfully acknowledged that the annotation process, which some of that goes away if you're going to be testing new architectures, although not completely because you need to know the right answer. But that annotation process is quite significant, particularly with tens of thousands of images, but has been done by work of specialty societies. So the neuro cases have been done by the Neuro Radiology Society, and so forth. So big activity that has put this on, and I think it has generated again the team sport that has been mentioned, and getting people from data science excited about doing this work in medicine. I want to flip the coin a little bit here, Ian, and for radiologists who are not you, who do not have a background in data science, what should they know about AI? Let's say that they don't have the science, the math, the computer science. What should they be know about AI, and how should they approach using these tools?
Yeah, I think it's always good to approach it with a bit of skepticism, especially in our space where the results could affect patient care and outcomes. And so if some company comes to you and says, I have this great product, has like an AUC of like 99 on our testing, and you should definitely use it. You could definitely explore that, but you want to ask questions about like what kind of data set it was trained on, they probably won't tell you. But just kind of like probe into a little bit more. And I think, what is helpful is just kind of understanding how these algorithms are built. And you don't really need to know a math or science, a lot of math or science like background to know like sort of the general idea, where it all really depends on like the data that it's trained on. Um, and so the quality of that data, the amount of data is really important. And also understanding that your data, which was not involved most likely in the training process, is potentially very different. And you have to look out for things that could, result in degradations in performance if you apply these AI algorithms to your own data. And so I think in these cases, it's just good to have a healthy dose of skepticism. And there's a lot of free material out there in case you're trying to advance your knowledge. So Andre Karpathy was at Stanford, and then Tesla, and then OpenAI has a lot of great videos on YouTube that are quite long, and some of them get a little bit technical, but they're a great way to kind of start peeking into that black box a little bit. And I think the most important thing is just knowing how to also evaluate these algorithms and like, how to interact with them. Like for example, typically they're not predicting like a binary output, even though that's oftentimes what's shown to you. Kind of understanding like what the inputs and outputs are. And a lot of that you can do without significant technical background.
Yes, and you're right. And we do actually have some educational materials for high level for folks who don't have computer science and machine learning that are online, internal. And then we do have series for our residents to teach them really to identify when these models can go wrong, how to use them, maybe read the literature and so on, which I think is very important. And there are other things that are maybe not as technical as some of the Andre Kopathy and so on, but the RSNA, for example, has educational activities that you can participate in that are very, very helpful to get a high level understanding. A corollary here to one of our discussions, have you tested any of your algorithms on MGB clinical data downloaded from PACS? Have you tried on our data, Dr. Pan?
I have not. I don't think I'm allowed to without like an IRB or anything like that. Um,
Yes,
but
you
I
need an
haven't tested
IRB.
any of the challenge models on the data. But I mean, my models are out there, so if someone wanted to do it under an IRB, they could.
And then a question here, are there publicly available data sets with de-identified patients in the electronic health record data available for AI model studies? How do you find them? And I would note the MIDRIC. I don't know if you're familiar with the MIDRIC data, Ian. But yet the short answer to that question is yes. But Ian, go ahead.
Yeah, I think there are a couple data sets. There's like Mimic, which has chest X-rays with radiology reports, and I think some clinical data as well. It's definitely not as common as just pure imaging data. I think part of it is it's just harder to amass that kind of data set. And it's also harder to de-identify text. Um, Especially if you're talking about things like patient notes, if you want to work with like clinical notes, it's incredibly hard to de-identify those completely just because people include a lot of stuff there. Um, in terms of how you find them, Midrick is a good resource because it's like a central data repository. I just Google things a lot of times and hope something comes up. But there are, like, for example, for pathology data, there's like TCGA. And so there are these central data repositories that you can look for.
Yes, and the TCGA is around specific diseases, breast cancer, prostate, I believe, colorectal cancer, maybe lung cancer, but you can apply, there's no fee, but you can apply to use those data sets. Ron Summers at the NIH has been very wonderful in sharing data from their institution, largely imaging data. But Dr. Pan is correct. It's very difficult to de-identify the electronic medical record data to be able to have institutions willing to sort of put those out and make sure that no patient privacy is exposed. Question here: what is the role you, me, aka the human, played in these challenges? It sounds very easy to you. It seems to me what you did is just to find a challenge topic from Kaggle and place it in Hugging and come out a prize. I'm not sure. Do you have time quickly, brief steps involving the beginners like me who dare to have a hand and maybe try to do this? I think the question is, how do you get started with doing these? There are a lot of tools, as Dr. Pan mentioned, in terms of Jupyter Notebooks, which you enable you to use a lot of libraries. So, for example, you would never have to program a convolutional. That's done by folks who have done it very well. There are lots of resources, but I think this person is really asking, how does someone get started as a beginner? What would your advice be?
I think just dive right in. So, when a challenge comes out, just make an account. It's free. And then just download the data and start playing around with it. Read the discussion forums, look at what people are posting in the notebook section. Of course, you need to have like some understanding of basic Python programming, but you can actually get that over the course of a competition. I think it's good to approach it with a goal in mind. Like my goal for this competition is just to gain some experience in Python, right? Like maybe I never actually train a model, but I at least learn how to like explore the data and things like that. Or maybe my goal is to just try and like keep up to date with what people are doing and try to understand what they're doing at a higher level, even if I'm never going to really dive into the technical stuff. Um, and then there are also free computing resources that you can use. So Kaggle supplies kernels with GPUs that you can use if you don't have your own. There's Google Colab. And so there are a lot of ways where, even if you just have a laptop that can't really train models on its own, you can just use the cloud resources that are freely available. There are obviously restrictions on sort of how much you can use, but I think it's a great place to start, and then you can kind of determine whether it's worth investing more time, effort, and money into.
Yeah, great. And Khalid Yunus here, who was a member of the team that developed the pneumothorax detection algorithm, with the GE Healthcare. One of the challenges that they faced was that competition-winning solutions often overestimate performance. metrics like area under the curve, AUC, without considering computational costs. Although I believe there's a limit on the computation for these challenges, such as inference time. And this tends to favor ensemble models that achieve high scores but are impractical for real world deployment. From your experience as a Kaggle Challenge winner, have you seen judging criteria evolve to account for computational efficiency, which is a reality in the real world, right? In terms of computing inference in a day-to-day clinical environment. What are your thoughts about balancing model performance with deployment constraints? That's a very interesting question.
Yeah, this is a great question and something I didn't really mention during the talk. So the winners of these challenges, including my own solutions, typically are fairly large ensembles. And ensembling is like one of the things I rely on most heavily to do well, where I train models that can be quite different from each other, but then I combine them. So there's a little bit more synergy there. But obviously that adds to the computational costs. There is a computational limit for the challenges. So typically it's like 9 hours runtime, which can be quite generous depending on the size of the test data set. But the way you submit your solution to these challenges, you don't get to see the data that it's actually run on. You submit code that runs inference on a few dummy samples, and then that code is run on that data sort of in the background. And so you're limited to like the available like GPU kernel they have, which is like I think quite an old GPU. Um, but I think what you'll find is there are a fair number of solutions that actually don't have that many models. And if you take like the best single model, it's still very good. And you can also like distill the sort of information from the ensemble into a smaller model. So a lot of smaller foundation models are trained through a process called distillation, where they basically take a very big foundation model and use it to essentially teach a smaller foundation model how to give good predictions or outputs. And so I think the actual winning solutions that may comprise a bunch of models in a large ensemble probably are not feasible to deploy depending on what your computational requirements are, and probably are not necessary because we're talking about like, 0.5% extra performance here, right? Because you're trying to win and squeeze every ounce of performance you can get. But at the end of the day, if you take one model from that winning ensemble, it's already going to be really good. And there are some challenges where there's an efficiency prize. And so it's like, for example, if you look at the top 50 or 100 solutions, like which one out of those, which one is the fastest, for example. And so some challenges where efficiency is actually really important for the final product will have that kind of as like a separate category that people can win.
Thank you. Interested in your thought, how do you benchmark generative AI or generalist AI models? It's kind of a difficult concept, and one concept people are using is, well, how do you sort of compare how a human performs, how a radiologist performs, and we do peer review and we do testing on board licensing exams and so on to assess performance of the human. What are your thoughts on how we start assessing real performance of the very exciting foundation models?
Yeah, I mean, if we're thinking about something like radiology report generation, I think that's a lot of what people are thinking about these days. There are certain metrics that you can use to try and quantify how well a draft report matches like an ideal sort of report or a ground truth report. They're not perfect. I think Pranav Rajprakash has worked on some of that as well. I think a lot of it just comes down to, comparison and then having a human sort of decide, um, which is, a lot of foundation models before were trained using something called like, I think it was reinforcement learning with human feedback. And so it's not quite that, but it's basically having a human evaluate, like for example, side by side, here's the model output, here's the human output. I don't know which one is which. Uh, are they similar? Do I like one more than the other? And then just seeing how it stacks up there. I think in terms of radiology specifically, there are things like, this is a clinically significant omission. Like there is a finding, it's clinically significant, and the model did not report it. Versus like clinically like not significant finding, and then also like hallucinations, right? The model said that there was free air in the abdomen, but there was not, right? That's bad because then the patient might have been taking the surgery when there's nothing there. And so, sort of thinking about how you can do it in a more structured way, you could think about like what errors are important and ways to sort of count those errors from the model, which, there is a little bit of subjectivity to that as well. But I think it's definitely an active area that people are still working on, and certainly a really important area when we're talking about, for example, getting regulatory clearance and then doing studies, potentially trials on like the effects of these models in the real world.
Yeah, no, fantastic. So, inclusion, exclusion criteria of things that have been put in the report or not put in the report, and some are important, some are less important. Well, I think we've run out of time, unfortunately, but I want to thank you for a wonderful lecture, Dr. Pan, and we appreciate all your contributions to these activities, and you're getting lots of kudos on the chat for a wonderful, wonderful presentation. So, thank you very much, Dr. Pan.
Thanks so much for having me.
All right, take care.